Okay, what do we do? What do we do with this? Now, when you look at problems like this, you can see that we've got numbers and we've got variables, and we've got to simplify the whole schmear, right? You might initially think.
Pay attention.
You might initially think that the variables are going to be harder, right? Because they're variables, but they're not. The variables are simple. It's the numbers that are the most complicated part. If we're going to simplify this thing, my recommendation would be, there's a lot of ways you can do it. I would recommend multiplying straight across the top and straight across the bottom, and then simplifying vertically, with the exception of the numbers. Sometimes with the numbers, if we were to do that, we would end up with 12 times 7 is, what, 84 on the top, 28 on the bottom, and 84 28ths is, I mean, we got to simplify that, and that's a big fraction to simplify, right? It would work, but wouldn't it be easier just because we're multiplying straight across, right? We're multiplying and dividing all these numbers. Wouldn't it be easier to cross-cancel and reduce these things before we get to this huge fraction? Do you see some reduction that we could do? Okay, for one thing, now if these were being added, then we couldn't do this, or subtracted, then we couldn't do this. But because they're being multiplied, we can. The 12 over 4 reduces to what?
It's a smiley face.
Yeah. 3 over 1, right there. How's that? So, and then what about the 7 over 7?
1.
Yeah, that's just 1 over 1. We can only do this if we're multiplying. Remember, we can't do this not for addition or subtraction. Can't do this stuff. Only for multiplication. But then the numbers we get when we multiply straight across, I'm just going to get a 3 on the top, right? And a 1 on the bottom. Agreed?
Yeah.
Okay, what about the other variables? If I multiply straight across, x to the 1 times x to the 5th is
X to the 6.
x to the 6th. What about the y's? Y to the 1, which is, there's really a 1 there, right? Y to the 1 times y squared is y cubed. And then on the bottom, we have a 1, which we wouldn't write. We wouldn't put the number 1 on the bottom ever. And then x to the 4th times x to the 7th, x to the 11th, and then it looks like just a plain old y. Okay? All right, so now this is pretty easy. The numbers were the hard part. The variables are simple. It was easy to consolidate the variables horizontally. It's just as easy vertically. So if I group them vertically, what do I get? What's x to the 6th divided by x to the 11th? What's my rule for that? Okay, I subtract, right? When we divide like bases, we subtract exponents. Now remember our rule, different than the book. What did we say about this? If I have a bigger power of x on the bottom than the top, what do I do?
It goes to the bottom.
Stays on the bottom. Good. So this is equal to, got a 3 on the top. On the bottom, I'm going to have an x to the 5th. 11 minus 6. It stays where it's the most powerful. The base stays where it's the most powerful. And we subtract away the other exponent. Another way to think about that, think of it as canceling away 6 of those x's that are strung out. So if I cancel 6 from the top and 6 from the bottom, I'm left with 5 on the bottom. Either way, same thing. Okay? What about the y's? Y to the 2nd on top, because I've got a y to the 1 on the bottom. So the y's stay on top to the 3 minus 1. And there's my answer. Okay, no big deal. Right? Okay. Very good. All right, so how about... Oh, all right. That is messy.
We don't have to do that, right? Sometimes.
Okay, adding, this is the stuff I said I was going to go through. I'll be real quick about it. Take a quick look at this stuff. Okay, adding and subtracting polynomials. Adding and subtracting polynomials is extremely simple. All you're doing is combining like terms. That's it. So if we want to add up polynomials vertically, let's say, if you're going to add them vertically, the only real rule is that you have to have a column for each power of x. So we've got a column for the constant, We got a column for x to the 1, column for x squared, column for x cubed. And then I just combine them, right? Negative 7 plus 8 is 1. Negative x plus 0 is just negative x. 2x squared minus 10x squared is negative 8x squared. 3x cubed plus x cubed is 4x cubed. Done. That's all there is to it. Okay, no big deal. If we add stuff up horizontally or subtract, same kind of deal. I'm going to do this a little differently than they do. I don't like the way they do it. But what do you suppose we do with this? It's probably the easiest way to do this. If I'm going to subtract these two polynomials. Okay, you're going to combine like terms. What do I maybe want to do first? Yeah, good. Distribute the negative 1. Right? And there's a 1 out in front of this one, so I don't even need those parentheses. Right? So what I'm able to do then is just write this as 8x cubed minus 3x squared minus 2x plus 9. And then distributing the negative sign does what? Yeah, it just changes all the signs. So minus 2x cubed minus 6x squared plus x minus 1. Combine like terms and we're done. So what do we get? If we combine like terms, 8x cubed minus 2x cubed is 6x cubed. So we can cross those guys off. Negative 3x squared minus 6x squared. Good. Negative 9x squared. So we can cross those guys off. Negative 2x plus x. Close. Negative x. Those guys are gone. And then 9 minus 1 plus 8. Okay, and that's it. Okay, no biggie, right? Okay, adding, same deal. If we add up polynomials, just add like terms. No big deal. Let's get on to multiplication. Okay, multiplying polynomials. Now, we can multiply polynomials vertically. That's fine. It's actually a pretty good way to do it. If we multiply them vertically, we'll line them up just like we would multi-digit numbers if we're multiplying out multi-digit numbers. The only thing you got to be careful of is when you get your answers down here, you need to have a column for the constants, a column for the x's, column for the x squareds, column for the x cubes, etc. Okay? We don't have to write them that way up here if we don't want to, but when we get our answers and we multiply this thing out, when we start getting answers, in order to be able to line them up vertically, we got to keep a column for each power. Yes?
Can we just plug it into our calculator and do plus?
How are you going to plug that in your calculator with x's though?
Where's the x one?
But it won't. Your calculators won't. There are calculators that would do that, but yours won't. 1084s won't do this. So when you want to multiply out polynomials, you got to do it. You got to do it by hand. Okay, so if we do this, then let's follow the progression of this problem. So we're going to multiply the negative 3 all the way through. We'll distribute the negative 3, just like we would with long multiplication. We'll multiply the first digit through, then the second digit through, etc. So negative 3 times 4 is going to give us our negative 12. Negative 3 times 2x gives us our negative 6x. Negative 3 times x squared is positive 3x squared. Now the x's. If I multiply the x through, x times 4 is 4x, so that has to line up in the x column, right? X times 2x is 2x squared, so it lines up in the x squared column. And x times negative x squared is negative x cubed, so that gets its own x cubed column. And then when we add up vertically, you get a negative 12, negative 2x, positive 5x squared, and negative x cubed, and we're done. Okay, no biggie, right? No biggie. What if we wanted to multiply horizontally? Also very simple. We would just distribute. Oops. We would just distribute from the smaller polynomial, the one with 2 terms, to the one with 3 terms. So we only have to distribute twice instead of 3 times. And so what are we going to get if we distribute the x here? x times 3x squared is 3x cubed. And I want to keep columns for each power of x now. X times negative 2x. Okay. Negative 4x. And then I could just keep going. Now I could distribute the negative 3. And I could either just string those all out in a row and combine like terms, and that's fine. Or I could combine them vertically. Negative 3 times 3x squared is negative 9x squared. So let's line it up in the x squared column. Negative 3 times negative 2x. Okay, 6x, good. Negative 3 times negative 4. Okay, and then we add those up. 12, what? 2x, negative 11, x squared, and 3x cubed. Yeah. Okay. Either way, no big deal. Okay, what if we have something like that? What if we're multiplying out 3 polynomials? They wouldn't even have to be binomials. What's the only thing we got to be careful about doing here if we're multiplying out more than 2 polynomials? When we multiply stuff together, we always multiply in pairs. Right? We can only multiply 2 things at a time. And so we'd have to multiply out 2 of these, get an answer, and then multiply that answer by the third, right? So every time you add another polynomial to this product, you're going to add another layer to that process. So what if we FOILed the first 2? Okay, we get that for our result. If we FOILed out the first 2. Then we'd have to just multiply that times x plus 3. So distribute the x all the way through, distribute the 3 all the way through, and add up like terms. Okay, not hard, not hard. Okay, so the last part of 6.3 is the one that I want to just take a second on. The product patterns. Now, we haven't done this a lot yet. This is the first chapter where we start to deal with product patterns. They haven't been a big deal in the past because it's not that hard. For example, look down at the bottom of the page here. If we're looking at products of binomials, well, big deal. I could just FOIL that out, right? And I'm going to get this answer relatively quickly if I FOIL out a plus b. It's a little bit easier, but not that much, to just know this pattern. However, when we start to look at cubes, it's a big difference. Cubing out a plus b means I've got to multiply a plus b times a plus b times a plus b. That's a double distribution there, isn't it? I've got to FOIL out the first, get an answer, then I've got to distribute those polynomials through each other to multiply them out. That's a lot of stuff to do. In this case, it's definitely much easier to just know the pattern. Okay, so as we start to get into bigger polynomial multiplication situations, we want to know the applicable patterns to save a lot of time and energy and effort. Okay, so I guess if we went back to this last page, it's not that big a deal, but I still think you need to know it. We know this pattern. This is what we call the conjugate pattern. If I multiply 2 conjugates together, and that just means 2 binomials with different terms between, or different signs between the terms. So if this one is a plus b, then that one's a minus b. If I multiply those out, I just get the difference of squares pattern. We did this in reverse in chapter 5. We started with the difference of squares and factored it into the conjugate pattern. Okay, we're just reversing it this time. So we know a plus b times a minus b is just a squared minus b squared. And an example would be x plus 3 times x minus 3. I know it's always going to be the first term squared minus the last term squared. Done. Okay. What about square of a binomial? A plus b quantity squared. Now we could FOIL this out, but it's just nice to know what it is. It always follows this pattern. It's going to be the first term squared plus 2 times the sum of the, or the product of the 2, 2 times a times b plus the last term squared. Okay? So you got to know this one. But here's what I want to show you. You only have to know one of these. You don't have to memorize them both. Why memorize extra stuff? Because you really don't want to memorize as little as possible. If you know that one, you automatically know this one, and I'll show you how. Okay, so let's take this pattern, and if I want to get the pattern for a minus b squared, isn't that just the same thing as a plus negative b squared? Okay, so all we got to do is we just have to substitute. We have to substitute a negative b for every place that we see a b up here. And that gives us this pattern. Because a plus negative b is the same thing as a minus b, right? It's a good trick. So what does that give us? Well, this term stays the same. What about this one? 2 times a times negative b. What is that? Negative 2ab. Right? What about this one? Negative b quantity squared. What's negative 3 squared? Positive 9. What's negative b quantity squared? B squared. Yeah, it's positive b squared, isn't it? And there's a rule for this. Here's the rule. Anytime there's a 1 up there, 1 is the power of b in this middle term. 2 is the power of b in the last term, right? If I take a negative number to an even power, what's my result always going to be? Positive or negative? Positive, right? So a negative number to an even power is positive. A negative number to an odd power is always negative, right? And so this last term is just going to look like b squared. Okay? So this is the formula. If I wanted to know what this is, yeah, a minus b squared is that. A squared minus 2ab plus b squared. But you don't need to know it. If you're using a negative number, just plug a negative number in for b up here. If it's a minus b, plug in a negative value for b. One formula does it all. Okay? All right, let's do a quick example of that. What if we have this? What if we want to square out 2x minus 3? Okay? Well, we're going to use this pattern. Okay, but what's a and what's b? Okay, a is 2x. What's b? Negative 3, right? So then we'll just do this. What do we get from those? A squared, what is the quantity? Is going to be the quantity 2x squared, right? Plus 2 times a, 2x, times b, negative 3, plus b, which is negative 3 squared. What does that work out to be? What's that first term? What's 2x quantity squared?
4x squared.
Yeah, it's 4, right? Because I have to distribute that 2 to both parts of the product, right? So 2 squared times x squared gives me my 4x squared for the first term. Now, what does this one work out to be? Good. I get a negative 12x. And then the last term? Good. Yeah. Yeah. Okay, what about this pattern? Cube of a binomial. And once again, you only have to know the top one. Bottom one you get for free. All you have to do to get the bottom one is just plug a negative b in, substitute negative b for b in the top equation, and you get the bottom one for free. Okay, now how does this one work? Well, you got to memorize it, but I'll show you there's a pattern here that you may not have seen at first. look at the powers of a. Now notice that this first term has an a cubed, the second term has an a squared, the third term has an a to the first power, and then the last term actually has an a to the 0, but we don't write it. Anything to the 0 is equal to 1, so why would we write it? But it's there, right? Look at the b's. The b starts off, or ends up with a power of 3. Next to last term is 2, then a 1, and then a 0. Now, what do all the exponents add to in each of those terms? 3 plus 0, 2 plus 1, 1 plus 2, 0 plus 3. 3. So all the power, the exponential power, starts off with the a, and then builds to the b, term by term. Okay. What about the coefficients? If we just look at the coefficients now, let's get rid of the exponent stuff. If we look at the coefficients, I've got a 1, a 3, and a 1. How do we remember that? Well, the 3 is pretty easy because the 3 goes with the 3. Whoops. The 3 goes with the 3. That won't always be the case, by the way. For this one, it is. And then here's the other thing you can remember. If I draw a line down the middle, it's symmetrical, right? I've got a 3 and then a 1 as we move away from that midline. Okay, so the coefficients are symmetrical, 1s and 3s, right? So if you just remember that stuff, you can build that formula pretty easily, right? Okay, so let's try your hand in. Okay, don't say anything. See if everybody can do this now. What is a plus b cubed? Okay. So what is it?
A cubed
A cubed
plus 3 a squared
Okay, A's are moving down. B's are moving up.
plus 3 a b squared
Okay.
plus b squared. B
Plus b
cubed.
cubed. Okay, so let's try an example then. What is 2x minus 5 cubed? So I guess we got to answer the question then. What is A and what is B? A is 2x, B is negative 5. Okay, so then we're going to get 2x quantity cubed plus 3 times 2x times negative 5, 2x squared, sorry, times negative 5, plus 3 times 2x times negative 5 squared, plus negative 5 cubed, right? So what is that? What is the quantity 2x cubed? Not 6. 2 cubed is 8. X cubed. Now what about this whole thing? That's a 2. So 6 times negative 5. Negative 30. Oh, hang on. Nope. No, it's not. Whoops. Forgot something. I did 2. The 2 has to get distributed to both the 2 and the x. So that's really going to end up being not 2x, but when I square them both, it's going to be a 4x squared. Right? Because we had to square it out. So now what?
60 x squared.
Oh, okay, good. So 3 times 4 is 12 times negative 5 is negative 60. Then there's an x squared. Right? Okay, what about this guy?
Negative 5 squared is 10.
Okay, no, is 25. Okay, so this one can get replaced by a 25. So 3 times 2, well, how about this? 2 times 25 is times 3? 150. So it's positive 150x. And then finally, negative 5 cubed. Well, 5 times 5 is 25 times 5. 125, positive or negative? Negative. Good. Because we have an odd number, or a negative number to an odd power. So there it is. Okay. Right? Okay, not so bad. Not so bad. All right. Okay, so now okay, if we had to solve that quadratic equation, what would you do? We won't even necessarily do it, but I want to know, what would your strategy be?
Quadratic formula.
Quadratic formula, sure. Quadratic equations in standard form are really easy to solve because either they're going to factor very simply or we won't bother. We'll use the quadratic formula, or the other possibility is, so that would be quadratic formula. No big deal. What if we wanted to solve, say, what about that one? What would we do with that one? Well, we can't distribute. Isolate it. Good. We can point to a single x, so therefore we can isolate it. Now we won't do it, but just tell me what would the steps be in order that we would use to isolate that. Okay, add 1. Good. That gets rid of this guy.
Divide by 3.
Divide by 3. That gets rid of that. Square root. That gets rid of that. Add 2. Okay, and when I square root, what's the one tricky part? Whenever I square root both sides, I have to plus or minus. Okay, done. So solving quadratic equations. Last chapter probably seemed like pretty hard stuff, but in hindsight, not so bad. We've got pretty good weapons for solving quadratic equations. Okay, but what do we do? What do we do with something like this? We don't know. We haven't talked about it yet.
Go up to Mr. West's desk and ask him.
No, he wouldn't help you because it's a test. This is the goal really of the main goal. There's lots of goals in chapter 6, but probably the big one is how do we solve bigger equations like that? Not quadratic, but bigger polynomials. And the answer is, honestly, the answer is with great care or not at all with a graphing calculator. If sometimes we'll be able to solve these things, but not in all cases. In some cases, solving them numerically, even though it's possible to get approximate answers, it's really hard to do and it's not always worth it. But this happens to be one that we could do. The only way we have to do this is to either isolate the variable if there's a single x, that would always work, but then find a way to factor the polynomial using about 4 different tricks, and that's about all we got. And then after that, we just wouldn't even bother. Okay? And so we're not going to get to that today, but I just wanted to draw a parallel for you. So this is parallel to the stuff we did last time. Remember that we started off solving quadratic equations by factoring the quadratic expressions and setting the factors equal to 0. We didn't have to do that very long, though, because we had an ace in the hole. We had that quadratic formula, but there is no cubic formula, unfortunately. Sorry. There isn't one. There isn't a quartic formula. The only show in town is you've got to factor the thing or not much else to do. Okay? Let's take maybe just a really quick look. Okay, we're not going to, I don't want to get very far through this at all. Yeah. Yeah. Okay, this is stuff we know how to do. Okay, we want to look at some ways to factor bigger polynomials. Well, Here's the easiest way. The easiest way is if they fall right into a factoring pattern that's really easy to apply and easy to remember. So for example, if we have the sum of two cubes, if I can write the polynomial out as the sum of two cubes, it's always going to follow this pattern. And we'll talk more about the pattern later. If it's a difference of two cubes, it's always going to follow this pattern. So if I can take my original polynomial, like this guy, x cubed plus 8, and I can write that as a sum of two things that are cubed, which I can, because I could write that as x cubed plus 2 cubed, then it follows that pattern. Okay. Here I could have written this as the quantity 2x cubed minus 1 cubed, and I could have followed this pattern. Okay. So we've got those possibilities. Okay. We've got some other things we can do. Let's skip this. Okay, we can factor by grouping, which we've already done. Factoring by grouping, I snuck in there in chapter 5 when we did the A times C then split B. That's factoring by grouping. So the hardest one of the techniques in chapter 6, we've already done. I just want to show that to you. So what if we wanted to do this guy? I just want to show you it's no big deal. Remove a little bit of the chapter 6 fear. It's not that bad. Okay, whenever we've got 4 terms in a polynomial, and you can almost, actually you can't. You can break down these strategies just by the number of terms that you're faced with. If I'm faced with 2 terms, that was those factoring patterns. Either they'll work or they won't. If I'm faced with 4 terms in a polynomial, the only thing I can try is factoring by grouping. Now, we always want to see if I can factor out a greatest common factor first, but there's nothing I can take out here, right? So let's just try this. You already know how to do this. If I break this thing up into groups, okay, what are my 2 groups? The first group is just this, right? I've got this group plus that group. What did we do going clear back into, early on in chapter 5 when we did the A times C then split B? What did we do to that first group? We broke it apart how? What did we do to that? What did we try to factor out of that first group? Well, in this case, it's going to be a what? X squared. We want to take out the greatest common factor, the biggest thing I can pull away from both terms. In this case, the biggest thing I can pull away is an x squared. I'm undistributing that. So what am I left with if I divide an x squared or undistribute an x squared? X?
Minus 2.
Yeah. Everybody see that? Remember this?
Yeah.
Okay. And then we said that if this factoring by grouping is going to work, if it's going to work, I've got to have the same thing happening in the second group. And in fact, the leftover factors have to be equal. So I know that this one has to be an x minus 2. It just has to. Now here's the part you got to hear. Adam, you got to hear this. So then the question is, if it's going to work or not depends on right here. Can I find a number to undistribute, to factor out from the second group that would give me that?
Negative.
In this case, it would be a negative 9, and so it does work. Now, it won't always work. In some cases, it wouldn't work, and we can't factor by grouping, and we can't factor, we're done. But in this case, we could, because x minus 2 does work with negative 9, right? And so then our answer is just, I could pull out the x minus 2, and if I do that, I'm left with x squared minus 9. Exactly. And then we haven't talked about that pattern. Well, actually, we did, going back to chapter 5. That's a difference of squares, isn't it? We'll review this again. I'm just giving you an overview. We'll spend more time on this later. Do you remember how that factors? if I have x squared minus 9, isn't that the same as x squared minus 3 squared? Right? And doesn't that, if it's a difference of squares, it breaks into x plus 3 and x minus 3. Remember that in the last chapter? Kind of, sort of, maybe? In fact, we just looked at that in reverse. Remember, we just said that if we multiply out a conjugate pattern, we get a difference of squares in that last slideshow we looked at, right? Okay, so then the last thing we could do is we could break this one apart into x plus 3 and x minus 3. What's that?
How do you call x squared? Obviously, how you might keep going to far left.
Oh, okay. Because what's the biggest power of x that I could divide away from the first two terms? I can pull away an x squared, but I can't pull away an x cubed because that one only has an x squared to give. Right. So all it's going to be ever is the biggest common power of x. Okay? And that's our answer. And honestly, that's darn near as hard as it gets for factoring right there. Okay? Not so bad, right? Okay, and then the last one that we'll see, and I'm just giving you kind of a speedy look at this, we'll focus more on it later, is quadratic form. Okay, what about something like this? No, not that one. I don't like that one. Let's look at this one. Okay, take a quick look. So if I've got this trinomial, 3 terms, that looks like chapter 5 stuff, right? I could factor out a 4x squared to start with. I could pull away a 4 and an x squared from everything, and that helps. If I pull out a 4x squared, what I'm left with is x to the 4th minus 5x squared plus 6. Now this is the part I want to focus on. We'll spend more time on this. But that is a quadratic form. It's got 3 terms, and now notice, the first term, the x is to the 4th in the first term, it's squared in the second term, and there's no x in the third term. Now, what we're used to seeing, in chapter 5, that polynomial would have looked like this. We would have probably written it instead as, we would have had something like x squared minus 5x plus 6, right? But now, instead of just plain old x's in there, x squareds and x's, what we're trading is, we're substituting for all those x's, we're plugging in an x squared, right? What is x squared squared? X to the 4th, right? X squared times negative 5 is negative 5x squared. You see, so this stuff down here, this x to the 4th minus 5x squared plus 6, we can just think of as being x squared whoops, hang on, squared minus 5 x squared plus 6, right? So you're thinking of it as being quadratic, but instead of in packets of plain old x, it's in packets of x squareds, right? You see the pattern? You almost have to just stare at it a little bit to see that. Does this factor? Kind of. Yeah. It's kind of like the calculus version of Where's Waldo. There it is. There he is. X squared, right there. Okay. Anyway, I'm going to stop there. I just feel like that's a lot of stuff. I want to give you an overview. We'll go back and look at each of those in more detail. All right.